expressing concentration of solutions. So what's the big deal? Well, if you don't do it right, according to some articles here, some people could get a dosing error and have some difficulty breathing, for example, right? So concentration of solutions and doing it right is pretty important. In a solution, what is the difference between a solute and a solvent? So Vivian, let's take a look at this. Okay, I'm going to dump some, I don't know, potassium dichromate. This looks like it's a ½ liter of water. Dump the stuff in there, right? We dump some in there. We have a concentration of 0.3 moles per liter. Which one is, what's the solute? The stuff I've dumped in, right, the potassium dichromate. And the solvent is the water. But, I mean, I could have dumped, the stuff you dumped in isn't a very good definition for solute, because I could have dumped the water into the potassium dichromate, those little crystals. So the best way to describe solute and solvent is the one that you have the most of in this mixture is the solvent. The one you have the smallest of is the solute. And that way it makes sense when you mix two liquids, because if one liquid is less than the other one, that'll be the solute. Okay. The book wants us to talk about hydration and how things dissolve in some solutions. Since we're talking about solutions, I guess it makes sense. So what's going on at the atomic level when sodium chloride dissolves in water? So here's our sodium chloride crystal. And what are these things floating around? Our water molecules, right. And notice what's happening here. Water's pulling away one of these atoms. But look how they're oriented around it, right? Are those the oxygens or the hydrogens? Oxygens, right? Because the hydrogens, because water's H2O. Those are the oxygens oriented around it. Then look what's going on here. So the sodium chloride crystal is slowly just decomposing and falling apart, but the water is doing it. So this process of dissolving and what we call hydrating has to be a lower energy than this crystal sitting here. Because that's what nature does. It always goes to the lowest energy. So this is a natural thing that's going to happen. But now this ion, oh, see if you can figure this out. Oh, let's go back a little bit. Which one is which? Which ion is this? Is this the sodium ion or the chloride anion? The only clue that you have, right? Well, it's bigger. That's a clue. The other clue is that the hydrogens are all oriented towards it. Chloride. Crystal's right. How did she know that? How did she know that this is the chloride anion? Right? Well, which one is bigger? Na plus or Cl minus? It's kind of a trick question. Because if it was just Na and Cl, you would guess Na, because Na is closest to Fr, the corner, right? Because things get bigger as you go down at an angle. So you'd say sodium, but it isn't sodium. It's Na plus, and it's Cl minus. Which one is bigger? Negative, right? So ions, cations, are so small, like a dot. I mean, that positive charge just sucks up the electrons to be nothing. You can't even, it's extremely small. But if it's negative, right, electrons repel. It's going to be huge. So the chloride anion is huge. Okay. Now in that picture, did I?
So Cl is bigger to you?
Cl minus, anything. I don't care if it's chlorine. Give it a negative charge, it's going to be bigger than any cation.
Got it.
Right, that's how it always works. And then, so Crystal said that big green ball And that's why the hydrogens are oriented around it. Because if you draw the Lewis dot structure for hydrogen, it looks like this because it's bent. It's got these lone pairs. It pushes everything out of the way. And what's more electronegative, oxygen or hydrogen? Oxygen. So you put the partial negative on that, the partial positive over here. Well, then it would make sense why these water molecules orient themselves the way they do around the chloride. Right? Because the H's have a partial plus. Chloride's a negative. So, and it's this big structure that starts getting developed. It's very loose because what type of interaction is this? This hydration, it's called. This is hydration or hydrating. What type of force is acting there? Jasmine, what type of force is this? Right, when you have this Cl negative and you have a partial plus on the hydrogen, so they're sticking together. Not H. You're on the right track, though. You're close. It would be H bonding. There's H bonding within water, but no, we're talking about the interaction not between water molecules, which is H bonding. We're talking about the interaction between water molecules and Cl minus. Not ionic, because water is an ionic. Water is not an ionic compound. It's going to be an intermolecular force. Dipole. Someone said it. Dipole. Because water's got the dipole. And it's kind of weird to think of chloride as having a dipole, but it's a huge dipole. It's very strong. So it's classified as dipole. You can't say ionic because that would make it super strong. You would never, if you drink salt water, you taste the sodium ions, you taste the chloride anions. So this shell of water that's around it has to get out of the way, right? So this is what chloride would look like, hydrated. Sketch what you think, so that's chloride. Let's switch this to sodium ion. Sketch how you would say the sodium ion is hydrated, right? So orient the water molecules around a sodium ion. How would they be oriented in solution? What would its hydration radius look like? Right? We're not going to draw all that many waters, but how would you orient the water molecules around there? The oxygens would be attracted to the sodium. Right. So draw the O's over there. And you pretty much just draw as many as you can fit in. And you can even draw more after that. Draw another shell of them. It just keeps going. Okay. Sabina, would you say that iron plus 2 or iron plus 1 would be more strongly hydrated in water? Which one? Why plus 1? Now remember, it's supposed to be what type of interaction? What do we call it that this hydration is happening on? Dipole. So what has a stronger, it's odd to think of iron having a dipole, but what would be stronger? Iron plus 2 or iron plus 1? Anybody? What would give a stronger dipole interaction? Iron plus 2 or iron plus 1? Iron plus 2 has twice the charge of iron plus 1. Wouldn't the iron plus 2 give it's stronger. It's much more positive charge, right? So in fact, it's twice as strong. Should be twice as strong the interaction. So iron plus 2. So more strongly hydrated would mean not only the interaction stronger, but I bet you that shell of water is even bigger. The orientation, so you don't have this free-flowing water around an iron plus 2. It's got all these water molecules clinging to it. Now that it's weak, but it's this big blob floating through the water. what is going on at the atomic level in a saturated solution. So what does it mean if it's saturated? Ooh, it's at its capacity to do what? Yeah, take in more solute, or in this case, take in more of this sodium chloride, right? They should have drawn a negative sign right here. That's why the chloride is so much bigger than the sodium ions, because it's an anion. So these are the chlorides. So what they're trying to say is this is a saturated solution. You've got these chloride anions, and they don't have any other ones drawn around, but here's one. And the sodium ions in solution, and it's falling apart at the same rate as it's being formed. So that's kind of what they're trying to show in this really brief video. All right, see how the sodium is getting deposited. It's creating the crystal, precipitating. There's the sodium and the chloride. And then others are getting pulled off. And the video needs to be better, but they're being deposited and pulled off at the same rate, okay, for a saturated solution. It's exactly right, Crystal. You can't hold any more. Can't hold any more solution. Well, if you can't hold any more solution, you can't hold any more of the ions in there. You can't dissolve anymore. How the heck could you have a supersaturated solution? Doesn't even sound possible, but it is. And it's really an unstable situation. And the only way to do it, here's a good example of how they did it. Now, what I wish they would have had a very quick video on how they made this first. Oh, it's really blurry, isn't it? Okay, it's a little bit better. So what they did is they dissolved a bunch of sodium acetate in water, and then they heated it up. If you heat it up, can you dissolve even more? Yeah. So they dumped in a bunch more, heated it up, dumped in a bunch more. So they got it really hot, and they dissolved as much sodium acetate as they could. And everything is crystal clean. There's no dirt, there's no dust, nothing. Then they slowly let it cool, and they didn't let anybody touch it, bump it, nothing, right? So this thing hasn't been touched in a long time, and it's at room temp. So it's just waiting. All these ions, these sodium and acetate ions, are just dying to come out of solution. You just got to give them a reason. So you could shake it. That would work. That would make everything come out of solution and precipitate out. Or you could do what they did. They're going to seed it. So they're going to drop in just one of these little crystals. It could be of anything. It could be of dirt, but they're going to drop in a little crystal of sodium acetate, which will work even better. Because all the ions in solution are just going to crystallize onto this little particle.
Wow. That little small thing?
Yeah, well, now everything is coming out of solution. That little small thing just initiated it all, right? So it's kind of neat.
It's really cool.
It's a lot of work to make this demonstration, so I don't. But it's neat. Okay. So here's the majority of the problems that you're going to see. And Danielle, we've got 4 ways to express concentration. We have molarity, molality, mass percent, and mole fraction. Okay, so each of these equations, there's how many variables? I think there's more than 2. I count 1, 2, 3. And in each one, do you see 3 variables? Everybody? Make sure you see 3 variables in every single one of these equations. So that means Tegan, in every homework question, every quiz, every exam, they're going to give you how many variables? If they give you 3, you automatically ace it. It's no question. They're going to give you 2. So you solve for the third, right? That's what's going to happen. So my suggestion is to, in this big book that you got, right after day 10, and I don't know what happened to page numbers. They disappeared. It used to have page numbers. So right after day 10 is this handout that says questions concerning exam number 1. Okay? And then there's this, below is the equation sheet given on exam number 1. This is the equation sheet I'm giving you for the first exam. I would take it and just tear it out of there and have this next to you when you go to the boards, when you do homework, when you do problems in class, because this is what you depend on, right? If it's not on here, well, then you have to know it. If it's on here, you have to know how to use it. So just work on this. Don't open up the book. Don't go back into notes. Get used to using this equation sheet. The exam is going to be much smoother. Okay? So let's try a few of these. How would you prepare 250 grams of an aqueous solution that is 10% sodium carbonate by mass? Now, first off, I want to work this through for you. First off, how would you prepare questions? That means you have to tell a story. You have to say, your answer is going to be something like, add, we have to calculate it, so many grams of sodium carbonate to, I guess, so many grams of water would be the easiest way to say it. That'd be the easiest way to do it. So you have a balance, you have some sodium carbonate, mass out some. You got that part. Mass out some water, mix the two. You'll have 250 grams of 10% sodium carbonate. So we have to figure out how to answer those 2 questions. So it has to be one of these equations, Crystal Munoz, and they had to give us 2 of those unknowns. Which equation are we going to be using? Perfect. Mass percent. Whenever you see the percent symbol, you know it's going to be mass percent. Okay. So Gabby, in this mass percent equation, which one are we going to solve for?
Mass of solvent.
Mass of solute. She had to kind of look ahead to see that, I think, because you had to see what was given in the question. That means the other 2 have to be given. All right? So how I start these out, I write the equation. Mass of solute over mass of solution. Don't forget to multiply it by 100. Okay? So I'm going to solve for mass of solute. So I'm going to leave that one alone, just write mass of solute again. Or you could write mass of sodium carbonate up there if you wanted to, right? Because that's what the solute is. You could do that. I don't know if that's going to confuse you more. But how do I know sodium carbonate is the solute? It's only 10%. Yeah, right? It's only 10%. So, N plus, it's always that way. Look at this. Mass percent of solute. Whatever's after the percent is always the solute. Okay, so I knew that the sodium carbonate was a solute. I have to know the other 2 variables, Jasmine. What do I plug in for mass percent? 10. What do I plug in for mass of solution, Danny? 250 grams. All right. So remember the diagonal story? All right. Diana, you remember how to do this? Whatever you're solving for, make sure it's on top. Either one side or the other. Is that part covered? Yeah, that part's covered. So how do I get solve for mass percent? What do I do? Where do I put the 250? Up with the 10. Where do I move the 100? Yeah, down here, down with the 1, diagonal. So always move along those diagonals when you're going from top to bottom. right? So my mass, it's already on top, so just leave it alone. Leave it on that side. It would be 10 times 250 divided by 100. So 10, that essentially just dividing by 10, you should end up with like 25 grams. So I'm ready to write my answer now. If I ended up with 25 grams, all right, that means, here's my answer. Add, how many grams of sodium carbonate? 25. To, how many grams of water? Well, 250 has to be the solution. So that's everything. 225. Okay. I think that's the shortest, easiest way to say the answer. There's an alternative that I would also say works, because you're just trying to explain it to somebody. So you could also say add 25 grams of sodium carbonate to water, right? And then add some water until you reach a total of 250 grams. That's a lot of English, though, right? So I add 25 grams of sodium carbonate to a beaker, then dump in some water until 250 grams is reached. So there's another way. But I think this is the easiest way, so we'll just leave it at that. Let's try one more of these before we get to the really, I think, the toughest one. Try this one. How many grams of HBr are in 25 mils of 0.18 molar HBr? See if you can find the equation. You're going to need some sunlight so you can do the calculator. All right. Find the equation. Rip out that cheat sheet. So Erica, which equation are you going to use?
Is it number 1?
Yeah, the big one. Big M equation. Right. But do you see the issue? Do you see the problem with this?
Yep. You're going to have to change those liters to grams.
Okay.
What?
Yeah, they gave you milliliters.
Oh, yeah.
So that's okay. We can get liters out of this. But they don't want moles. They want grams. So you see the two-step problem. First, solve for what? Solve for the moles. Solve for the moles. Second step, convert moles to grams. Using, what is it called? Molecular weight or molar mass, right? Molar mass. So 2 steps. First, solve for moles. Second, convert moles to grams.
Okay. So go one way and then go back the other way.
So you got to solve for moles using this. Okay. So you know 2 of those. You know the big M, you know the big L. Well, the big L is in the wrong units, but you can convert it. If you're not sure, just ask, and I can help you out. even have a calculator. Someone borrowed it and didn't give it back. Oh, wow. Last class period. So what'd you get? What's 0.025 times 0.18? 4.5 times 10 to the what? Negative 3. Okay. So did you get that far? Okay. Now we're ready to convert. Oh, 4.5, not 4.25. Sorry, thank you. Bromine. Bromine is about 80, well, 79.9 plus 1, 80.9. And then I'll have my grams of HBr. That are in 25 mils of 0.18 molar HBr. So anybody get a final answer? Gabby, what'd you get? 0.36. Anybody else get 0.36? Okay. So not too bad, right? So you pick the equation, you know 2 out of 3. And sometimes you might have to convert your answer to the units that they want. Okay? I think this is this is the ugliest one I can give you. This one there's a twist in. This is the only one there's really a twist in. Okay? Let's take a look at this question. Fructose is a sugar occurring in honey and fruits, the sweetest sugar. It's nearly twice as sweet as sucrose. How much water should be added to 1.75 grams of fructose to give 0.125 Molar solution? Oh no, this isn't that bad. This isn't that bad. Sorry, I thought this was going to be a confusing one. Jerixa. Oh no, you guys work on this. Do that. You want to go to the boards? Jeez. All right, so go ahead and work on this. If you get stuck, ask. Well, what equation, Crystal, did you start out with? Modality. Okay, so little m modality is equal to what over what? Oh, okay. Now you're over kilograms of solvent. Okay. So Crystal's asking. So we got to find the moles of. I think your question was right.
Was it?
What did you ask? Do you have to find the moles of? I was just trying to give some background. I don't want to confuse you, so that everyone's on the same page.
So we're going to solve for, we're solving for moles of solvent.
They want to know how much water should be added to 1.7, which is, I guess we got to figure out what's the solute and what's the solvent. Right? They're only adding 1.75 grams of fructose. And water almost is always the solvent, right? When is water ever going to be the solute? So, but they're adding a dinky amount of fructose. So if it helps, we could change these. Instead of writing solute, write C6H12O6. Instead of writing solvent, we could write water, H2O. And that really seems to help, I think. Because what will be the units of your answer? Danielle, what would be the units of your answer? Anybody see it? They want to know how much water. They didn't tell you the units. Kilograms. You're going to come out in kilograms. Fine. They didn't care. They didn't specify, so leave the answer in kilograms of water.
So we find the moles of the C6H12O6.
Yeah.
That's where I'm at.
With the 1 point. And that was your question at the beginning, and it was dead on. You're going to have to convert those 1.75 grams of fructose into moles. I just didn't want to say yes, and then no one else would be following you. So if you're not sure, just ask, and I can point you in the right direction. Do you have one of my calculators? You gotta get used to using mine.
Yes, it's
Oh, I don't even have. Someone borrowed mine. They didn't give it back.
I just told you right now.
Oh, you borrowed it?
I borrowed yours.
Oh.
Oh, okay. Why isn't it that good? Maybe under my phone.
So Sabina, I'm gonna cheat. What'd you get per molar mass? 180.18. Did anyone else get 180.18 for the molar mass? Okay, good. .71 times 10 to the negative 3.
Oh, is it 1.75?
Is that what you got? We have 0.97. 0.97 moles. I miswrote that. So it's 0.97? See,
Yeah.
Jerix, I need my calculator.
No, you have your head.
I can't be cheating.
You said you had your head, so. Told you. You know, it's not always there.
Anybody else get 0.97 moles?
It's one. I got one. Yeah, because it's 1.75 divided by 1. You get rid of 9.7. Oh, sorry.
So you were right,
Because I
Sabina.
did that the first
How would I doubt you?
Wow.
Right? Then solve for kilograms of water. So move kilograms of water to the top. The 0.125 to the bottom. Right? So Crystal Zamora, what'd you get as a final answer? Did you get it?
Yes, I got 0.077.
0.0. Anybody else get 0.077? Excellent.
So rounded it. Oh,
0.08. That's okay. So somewhere around there. Because we're not worried about sig figs. Okay.
Don't forget your units.
Yeah, kilograms of water.
No, I'm saying.
Oh, on here, what I do this on purpose. I leave units out here because I think it's easier for y'all to move stuff around, right? If you want to put the units in, do that. But I think folks have trouble enough with the math. So by writing down the equation, we're verifying what the units have to be. So when I put a number in, I already verified it.
Yeah, I see.
So try this one now. The caffeine problem. I know I changed the numbers in your book, but. Well, let's just answer question 3. Which one would you circle? Would you circle magnesium or aluminum? Which one would have the greater energy of hydration? It's a quick one.
Sorry.
It was one of the initial questions.
Oh.
What would have a greater energy of hydration? Mg plus 2 or Al plus 3? Al plus 3 because it has a higher charge. Okay, so just try the caffeine question. If you're not sure where to start, just ask.
So this one will given the kilograms of solvent.
Yes.
Or the grams.
Just to the wrong units. Exactly. But your thinking, Crystal, is right on. This time you're given the kilograms of solvent. And she's looking at this. She knows she's going to convert it to kilograms. That's why she said kilograms of solvent, because she knows how to convert that. Good. You're given the kilograms of solvent this time. Very good. Because it's a molality problem. That should be your starting point. I think it's easier if you put in what the solute and the solvent is, but what'd you get? See what the folks around you got.
Well, it's, yeah. It's the same number, it's just. Did you got the moles of the solvent first? What was that? And then what was the case solute?
Oh, what's 0.0946 times 0.045? Right, you had to multiply this times that. It's 2.1? This times this? I don't think that's 2.1. No, it's times. You have to take this times that. You have to bring it up to the top. That's where you messed up. Yeah. 4.257 times 10 to the negative 3. So last step, get it into grams. C8H10N4O2. Oh my goodness, what's the molar mass of that stuff? What'd you get? 194.22. Did anybody else get that for a molar mass? Okay, excellent. So your final answer, Sabina, what'd you get for a final answer? 0.8583. Sounds good enough to me. Okay. So come by. If you have some questions, I'll be glad to help you out with these problems. Give them a shot first.